Hello, welcome back to Analog Electronic Circuits lecture 10. So, in today's lecture we are going to continue from where we left off in the last class, and we are going to discuss swing limits. Okay. So, in the last class what we were at the end looking at, so we had in detail discussed the three different topologies: common source, common gate, common drain circuits. We had discussed input impedance, output impedance. We worked on two important formulae that I hope you have memorized, right. One is the impedance looking into the drain when the source is terminated by a resistor, and the other is the impedance looking into the source when the drain is terminated by a resistor. In both cases the gate is grounded. So, in the first case where you look in from the drain, impedance multiplies, whereas when you look in from the source, impedance gets divided. Okay. So, these are a few things that we had looked at. Then we looked at the source degenerated amplifier, where you start observing what happens when at the source you have a resistor and do not have a short to ground, which is usually the case in the common source amplifier. So, these are the different topologies of single transistor amplifiers, right. And we are now going to proceed with a discussion where the signal is no longer small. So, in general, all the discussions before this, where we worked out the gain and so on and so forth, these were all small signal, right. All this analysis was done in the incremental picture. So, if I incrementally increase, if I incrementally change the voltage at the input, what is the incremental change at the output? So, that is what we had looked at so far. What happens when the change at the output is no longer incremental? So, let us try to understand what are the limitations of our circuit, and these limitations are called the swing limits. So, let us look at the circuits one by one. So, first of all, our biasing circuit is common. It does not matter what you are doing, common source, common drain, common gate, we use the same core structure to establish the DC operating point. And we had a long discussion on why this structure looks like this, right. So, this side you establish the voltage at the gate, and this resistor is important because otherwise the current is too sensitive to this voltage, right, to this operating point, to this precise voltage, the current becomes overly sensitive. To reduce the sensitivity, we place this resistor, and now you know you have got a much more stable DC operating point. Okay. Then on top of this, we had all the capacitors, right. This is your input capacitor, this is your output capacitor. So, I am drawing the common source amplifier, and this is a capacitor which clamps the voltage at the source to a fixed value. Okay, this is our setup. Now, the question is, I am going to be changing the voltage over here. Okay. That is going to change the voltage over here. That is going to change the current, right. The DC current is going to still flow through the resistor. The small signal current, or rather the incremental current, is going to come through the capacitor, right. All of this is going to hold true no matter what. Now, this MOSFET has to be kept in its flat region of operation, otherwise what? Otherwise, the understanding, the basic understanding of the MOSFET, the GM for example of the MOSFET, no longer is what it should have been. Okay. The MOSFET is no longer going to reside at the nice operating point that you had set. So, remember you had set the MOSFET at an operating point, right, but you need to remain in the flat region of operation, otherwise the slope of this line is going to become low and therefore, the gain is going to not become enough and so on and so forth. So, the largest change in the drain voltage, in the drain to source voltage that you can have, the largest change is so much, right. Beyond this you are not allowed to change the drain voltage. Okay. So, that is one point, one extreme. The other extreme case is, remember when you are changing VGS, ID itself is changing, right. So, you are picking different curves from this family of curves and so on, right. You should not pick an ID that has dropped all the way down to 0 or lesser, it can't, ID can't go below 0, all right. So, you have to make sure that number 1, your device is in its flat region of operation, and number 2, the current through the device is more than 0 under all circumstances. So, these are the two extreme conditions. So, remember these are two and only two extreme conditions, everything is going to be depending on these two. Flat region is called saturation. So, what is the condition for saturation? VDS has to be more than VGS minus VT. This is the condition for saturation, okay, mathematically. And number 2, what else do you need to make sure? You need to make sure that current is always more than 0, and this has to happen throughout the cycle, right. These are the two extreme limits, right, one on the top. If I increase the current too much, then what is going to happen? If I increase the current through the MOSFET, then this voltage is going to drop, this voltage is going to increase maybe if this resistor is there, if this resistor is not there, then it is fine, this voltage is clamped, but the drain voltage is dropping, right. You have to make sure that VDS, even though the drain voltage has dropped, VDS should be sufficient that it is more than VGS minus VT. Okay. This is when the current is too much, and then the current is too little, right. The lowest current that you can have is 0, you can't have a current less than 0. All right. So, these are generally the two conditions which you have to maintain, right. Now, for example, let us take an example. Let us say that okay. So, this is your circuit, all right. Now, Suppose the power supply is 5 volts and then you are given that this MOSFET has Vt of 0.5 volt, okay, and this MOSFET requires ID equal to 1 milliampere. This is the DC operating point current is 1 milliampere, and these are the requirements. Fine. And then you have to make sure that you get let us increase some conditions. So, let us say that what is lambda? Do you know what lambda is? Did we discuss lambda? No? Okay, we will discuss just now. Okay. So, lambda will give us, you see the MOSFET has two basic parameters, one is GM and the other is GDS or RDS, right. GM effectively, if you know ID, if you know ID and if you know Vt and if you know something a little more about the MOSFET like K times VGS minus Vt the whole squared, that is ID. So, if you probably if you know K, then all of this is sufficient to tell you, to give you information about GM. Okay. But which is the piece of information that gives you RDS or GDS? It is going to be lambda. Okay. Lambda will tell you a little bit about the value of RDS. So, with the help of lambda you can find out RDS. Okay. Let us forget lambda for now. Let us forget lambda. Let us say RDS is infinite of this particular MOSFET, forget it. Okay. So, I have this MOSFET, I need a K. So, I need a K over here. I can't, I mean I am trying to construct this problem for you from the top of my head, I am trying to construct it. So, therefore, let me tell you what my thought process is. So, K times VGS minus Vt the whole squared is ID in the flat region. If I want to keep ID to be 1 milliampere and a very reasonable value of VGS minus Vt is 0.2 volts and there is a square. So, that is 0.2 into 0.2, that automatically means that my K should be 1 milliampere divided by 0.04. So, K should be 25 millisiemens per volt squared. Millisiemens per volt, I am sorry. Fine. So, suppose this is the MOSFET for you. Now, since we back calculated, I already know what is VGS minus Vt. VGS minus Vt is going to be 0.2 volts, which means that I need 0.7 volts over here. Okay. And I know ID is 1 milliampere. So, this 1 milliampere current is going this way as well as coming through this, right. So, this is 1 milliampere times Rs, this is 1 milliamperes times Rd, and therefore, Vds is 5 volts minus 1 milliampere times Rs plus Rd. in this case. Fine. Do you understand what we are doing? 5 volts, right, RD times 1 milliampere, RS times 1 milliampere, the remaining part is VDS. So, VDS is 5 minus RS plus RD times 1 milliampere. Any questions so far? Okay. So, next what we are going to do is, we are going to say that the input is going to oscillate. When the input oscillates, the output is going to, so if I have a sine wave at the input, I will have an inverted sine wave at the output, because the gain of this amplifier is minus GM times GM. So, there is a GM current which is caused by VGS. So, if I incrementally change this voltage over here, at the gate I incrementally change, at the source the voltage is constant. So, this VGS is incremental change across the MOSFET. This creates an incremental change in the current, right. How much? GM times VGS current is going to be produced, right. And let us say RDS is infinite. So, in that case all of this incremental current is going to come from RD, which means that the voltage here is going to be minus GM times RD. If I incrementally change this voltage by V, then the voltage here is going to be incrementally, it is going to change by minus GM times RD times V. Is this okay? And what is GM, by the way? ID is K times VGS minus VT the whole squared. So, GM is how much? 2K times VGS minus VT, which was 0.2, right. VGS minus VT was 0.2, 0.2 times 2 times K. So, 0.2 times 2 is 0.4 times K was 25 millisiemens per volt, right. 0.4 times 25 is 10 millisiemens. Okay. So, let us say you want a gain of 10 minus 10, in that case what should be the value of RD if you wanted a gain of minus 10? GM times RD is the voltage gain, GM is 10 millisiemens. So, therefore, RD should be 1 kilo ohm. Fine. Okay. What about RS? Let us pick RS also equal to 1 kilo ohm. Let us just pick. I really do not care what RS is. RS was just for stabilizing that value over there. So, let us put RS also equal to 1 kilo ohm. Okay. Now, what happens at DC? By the way, what are R1 and R2? This is 1 kilo ohm, 1 milliampere. So, the drop across this is 1 volt. So, the absolute voltage over here, the DC operating point voltage at the source is 1 volt. The DC operating voltage at the gate, so this VGS is 0.7, this is 1, so this is 1.7 volt. And what is the voltage at the drain? 1 milliampere current is coming from the top, right. This is 5 volt. So, automatically this means that this is going to be 4 volts. Okay. Now, just check that VDS is more than VGS minus VT. VGS minus VT is 0.2 volts, right. Is VDS more than 0.2? Yes. VDS is 3 volts over here, which is much more than 0.2. So, you are safely in the flat region of the MOSFET. In fact, your power supply could have been much lower. Okay. This also tells you how to choose values of R1 and R2, right. For example, R1 and R2 could have been 330 kilo ohms and 170 kilo ohms. R1 and R2 could have been 3.3 mega ohms and 1.7 mega ohms, for example. That will still give you 1.7 volts. Okay. You do not need too much current in this path, unlike in BJT circuits, which you might have studied elsewhere. In case of the MOSFET, you do not need too much current in this path, because the gate is not going to take any current whatsoever. Okay. So, this is the plan. Now, what are the limits of the incremental voltage and the incremental current? So, number 1, VDS, or rather the drain voltage is at 4 volts, source voltage is at 1 volt. Now, when I say VDS, this is really small VDS plus capital VDS. Agreed? And capital VDS I know is 4 volts minus 1 volt, capital VDS is 3 volts. Okay. So, when I am changing incrementally, when VDS is changing, by the way, what is small Vs? Small Vs is 0, because this capacitor takes all the incremental current. Okay, this capacitor is a short circuit for incremental current. So, small Vs, V sub small s is equal to 0. So, this is nothing but small Vd minus 0, they are the same in this case, because there is a capacitor between source and ground. All right. And this is the same as the output. Fine. Now, I need to make sure that this drain to source voltage is more than VGS minus VT. Okay. Now, in this case, the gate voltage is also going to be changing. When the gate voltage increases by 1 millivolt, the drain voltage decreases by 10 millivolts. That is what it means by having a gain of minus 10. All right. So, be careful over there. If so, once again, small VGS minus VT, small VGS comprises of small VGS plus capital VGS. Okay. And this capital VGS is how much? 0.7, VT was 0.5. So, this portion is 0.2, we know this. Once again, source is not changing. So, therefore, this is nothing but small Vg. Okay. So, what do I have? I have the following: V out plus 3 volts, that is my small VDS, has to be greater than small Vg plus 0.2. Okay. So, one shortcut is to say that small Vg is very small and you forget it, right, in which case the V out has a limit, right. V out has to be greater than minus 2.8 if you say that small Vg is very small, right, and that is a limit when the gain is that can be said when the gain of the amplifier is very large. So, if you were thinking of a gain of 100 or so, then you know Vg can be very small. In our particular case, the gain is only minus 10, in which case if V out changes by 10 millivolts plus 10 millivolts, Vg will be minus 1 millivolt. If V out is minus 2.8 volts, then Vg is plus 0.28 volts, and so on and so forth. So, you can call this approximately minus V out by 10 approximately, in which case now you move the V outs together. So, V out into 1.1 is greater than minus 2.8. Okay. So, it is not just V out is greater than minus 2.8, V out into 1.1 is greater than minus 2.8, and this will give you V out has a limit, it has to be more than minus 2.8 by 1.1, whatever that is, right. So, minus 2.8 by 1.1 would be approximately (2.6) minus 2.6 or so, something like that. Okay. Any questions so far? So, just by observing that the drain to source voltage has to be always greater than gate to source voltage minus Vt, I found a limit as to how much can possibly be the amplitude of V out. V out can't dip by more than minus 2.6 volts, because then if it does so, then the MOSFET will move out of saturation. It will fall into the linear region of operation, and that is not very good. Okay. Our next critical condition is that the current has always got to be more than 0. So, this is the second critical condition. So, the first critical condition we have looked at. The second critical condition is that the current has always got to be more than 0. Now, what does that mean? That means that this total ID has got to be more than 0 no matter what you do. But what is ID? ID is capital ID plus small ID. Okay. So, if capital ID we know it is 1 milliampere in this case, then small ID has a limit, small ID has to be more than minus 1 milliampere. It has to be more than minus 1 milliampere, it can't be less. Okay. If small ID is more than 1 milliampere, then what? So, this is capital ID goes this way, small ID goes that way. So, it splits up, right. So, what happens here? This is at 4 volts already because of capital ID. Now, excess dip is because of small ID. So, the drain voltage is going to dip further because of small ID, right. Effectively, I have got 5 volts over here, and this current is capital ID plus small ID, that is the total current. So, the voltage at the drain is 5 minus capital ID plus small ID times RD, right, that is the voltage at the drain. Okay. And now, this is 1 milliampere, this is 1 K. So, 1 milliampere and 1 K is 1 volt, 5 minus 1 volt is 4 volt, minus small I d times R d. And small I d has a limit that it has to be more than minus 1 milliampere. So, what does that mean? The minimum value of small I d is minus 1 milliampere. So, the smallest value of small I d is minus 1 milliampere. That means, the largest value of V d is how much? 5 volts. R d is 1 kilo, right, minus 1 R d, right, another minus. So, this whole thing is a plus 4 plus 1. So, V d, the largest value of V d is 5 volts. Look at it again, there is something trivial going on. The smallest value of I d plus small I d is 0, that is the lowest possible value of the current, right. And when that is the current, what is the drop across R d? 0. So, the largest voltage over here is nothing but 5 volts. Is this okay? Okay. Right now it is trivial because there is no load, but as soon as a load comes, this is not going to be the case anymore. So, you have to do it this way. Okay. So, this is the correct way of doing it. You can't just say that it is 5 volts. All right. Now, this happens to be 5. So, the largest value of the drain voltage is 5 volts, which means that the maximum V out is how much? Is 1 volt, because V out is what changes from the drain voltage steady state, right. Operating point of drain voltage is 5 volts, 4 volts, and then beyond that the drain voltage can go all the way up to 5. That means that the excess is limited to 1 volt. So, this tells you the two limits. Okay. So far so good? All right. Let us change the problem slightly, slight change. Let us put a load over here. Okay. So, first thing we are going to do is we are going to make this 2K, 2K. We will target a bias current of 1 milliampere, an operating point of 1 milliampere, operating current of 1 milliampere, 1K, and this is 1 milliampere, 1K. So, 1 volt over here. Volt power supply, and what is going to be the voltage over here? 1 milliampere, 2K. So, the voltage over here is going to be 3 volt, okay. And we are going to use the same parameters for the MOSFET. So, the same K and the same VGS, VT, the same VT, right, and that will tell me that the VGS is 0.7 volt, operating VGS is 0.7 volt, which means that the DC operating point over here is still 1.7 volt, and then R1 and R2 you have selected accordingly. Okay. So, this is the situation. Okay. Now, what is going to happen? Let us find out the limits. Limits are how high can V out go and how low V out can go. What is the lowest value of V out? What is the highest value of V out? Okay. And usually you will get these limits with the help of two conditions. Condition number 1 is that VDS has to be more than VGS minus VT at all times. Condition number 2 is ID has to be more than 0 at all times. So, these are the two conditions that you have. Fine. Okay. So, condition number 1, VDS has to be more than VGS minus VT. By the way, what is the gain of the amplifier? Look, it is the same as before, it is still minus 10 because I have got 2K in parallel with another 2K at the output. Okay. GM is still equal to 1 millisiemens, sorry 10 millisiemens, right, and the output impedance is 2K in parallel with 2K. I am assuming output impedance of the MOSFET to be infinite, RDS is infinite, let us say. So, the gain is still minus 10, all right, in which case if I have if I decrease the output voltage by 10 millivolt, I will have to increase the input voltage by 1 millivolt, that is what it means. Now, once again VDS has to be more than VGS minus VT at all times. VDS is comprised of drain voltage and source voltage. Source voltage is fixed at 1 volt, there is nothing. Where VDS is 2 volt in this case. And this has to be more than VGS minus VT. VD is the same as V out. VGS is 1.7 plus the input and VT is 0.5. I am sorry, gate voltage is 1.7, source voltage is 1 volt. So, VGS is 0.7 volts, VT is 0.5. So, VGS minus VT DC operating point is 0.2 and then the extra VGS on top of it is V in. And going by the gain that we have computed, V in is nothing but minus V out by 10, okay. And this gives you, you put all the V outs together, this has to be greater than minus 1.8. So, V out is more than minus 1.8 by 1.1, whatever that is, right, 1.6. Fine. So, this is condition number 1, that drain to source voltage has always got to be more than VGS minus VT. Condition number 2 is that the current through the MOSFET has always got to be more than 0. So, the current through the MOSFET is 1 milliampere, that is capital ID plus small ID, that is the current through the MOSFET. This has to be more than 0 at all times, which means small ID has a maximum small id has a minimum, right. Small id always has to be more than minus 1 milliampere. This is the requirement. Fine. Okay. So, now what is small id? Small id is the current through this capacitor. This is capital ID, this is small id. Okay. And small id creates a voltage drop over here by how much? So, a portion of small id comes this way, a portion of small id comes that way. So, this is capital ID plus the small id split is equal small id by 2, right, and this way the current is small id by 2, okay, because 2k and 2k, right. I am just trying to understand the situation. The net current is capital ID plus small id, okay, which again splits up into the capacitor and the resistor at the source. All right. Now, small id by 2 is the current, the signal current coming from the drain resistor. Small id by 2 is the signal current coming from the load. Fine, it is an equal split because these two resistors are equal, happen to be equal. What is going to be the change in V out? What is the relationship between V out and small id? Yes. So, the drain voltage is, the change in the drain voltage is V out. What is the smallest value of small id is minus 1 milliampere. Okay. So, therefore, the smallest value of the current of this of this particular current through this resistor is 1 milliampere plus minus 0.5 milliampere. Okay. So, the lowest value of this particular current is half a milliampere. So, this particular current lowest is 0.5 milliampere, it can't be lower than 0.5. Do you agree? Do you see what is going on over here? The entire DC current cannot be the signal current, only portion of it is coming through this resistor, the other half of it is coming from the other resistor. Okay. So, the lowest value of this total current id plus small id by 2, the lowest value is only half a milliampere. Okay. Capital ID is 1 milliampere. The smallest value of small id by 2, the least value of small id by 2, the least value of small id is minus 1, the least value of small id by 2 is minus 0.5. So, the least of the total is 1 minus 0.5, which is 0.5 milliampere. It can't be lower than that, which means that the least drop across this resistor, the smallest possible drop, okay, is 0.5 times 2k, which is 1 volt. That means that the largest voltage that the drain will ever go to is 4 volts, the largest voltage. It can't go higher than that, because the smallest drop across this 2k resistor is 1 volt. So, you want it written down? Okay. So, the smallest value of ID is minus 1 milliampere, then the smallest value of the largest value of VD, VD is what? VD is 5 volt minus capital ID plus small ID times RD. Sorry, small ID by 2. Okay. And here you are saying that small ID has a smallest value of 1 milliampere, it is always larger than that, and therefore, VD has the largest value. You plug in capital ID 1, small ID minus 1, right, 1 minus 1 by 2. So, this is half, capital RD is 2 kilo ohms, half times 2 kilo ohm is 1 volt. So, the largest value of VD is 4 volts. Okay. You started from 3 volts, the largest you can reach is 4 volts. That means, V out is 1 volt. Okay. V out is nothing but small VD, V. Okay. All right, is this kind of understood what's going on over here? So, all of your circuits, all the circuits that we have studied before, you will have this kind of a pattern. The pattern is that the circuit is limited on two ends. One is what is the largest value of the output, the other is what is the smallest value of the output, right. You are looking at this inequality. The largest value of the output is 1 volt, smallest value of the output is minus 1.6. So, these are the limits of the output voltage. These two are always going to be dictated by two conditions. One is what is the voltage VDS, this VDS has always got to be more than VGS minus VT. This is condition number 1, and condition number 2 is what is the current through the device. This current has always got to be more than 0. Okay. And based on these two conditions, you will get these two limits. Now, when you have more than one transistor in the circuit, so far we have not seen more than one transistor. Even when you have got more than one transistor, the same rules apply, right, but then you have to take the conditions, two conditions for each transistor. So, 4 conditions. Some of those 2 conditions will not be relevant because they will overlap, and you will have only 2 extreme limits, and those 2 extreme limits will give you the largest and smallest possible values at the output. So, these are the swing limits of the circuit. Okay. Quick thing, what happens if this capacitor was not there, if there was source degeneration? Shall we quickly think of one? So, let us do a complicated one, right. So, let us say this is 10K, this is 10K and this is 1K. Okay. And let us say that this voltage over here is 5 volts, VDD is 5 volts. And let us budget for the DC operating point, let us budget what would be a nice number, 3.9 volts would be nice. Of VDS at DC. Okay, so DC operating point I am going to budget, this is just I am doing a budget. Okay, so 3.9 volts over here. So 1.1 volt between these two resistors, which means I can afford a current of 0.1 milliampere. So this current is 0.1 milliampere at DC. All right. So this is where we start from. Now, just by the way, what is the gain of this circuit? What is the voltage gain of this circuit? Do you know? This is the source degenerated amplifier. Yesterday in the last class we had looked at the expression for this source degenerated amplifier. The expression was quite complicated, but when you say that GM is very large and GDS is very small, some strange things happen, lot of things disappear, and finally you end up with the gain as minus RD by RS. Okay. So, how do you figure that out? You say that the voltage at the source over here is going to be pretty much equal to the voltage at the gate. So, if I apply V in at the gate, then the voltage at the source is also almost equal to V in. So, the current through the source resistor is V in by 1 K, V in by the source resistance. This current has to come from the top. Now, from the top means you lump these two resistors together, right. Obviously, it is going to split up between those two resistors. So, that signal current is V in by 1 K. That signal current has to come from the top through the drain resistor, right. So, the voltage at the output is minus R D times V in by R S, okay, or in other words the voltage gain is minus R D by R S, where R D is in this case 10 K parallel 10 K, 5 K. So, this particular circuit will have a gain of approximately 5, it is actually going to be less than 5, right, somewhat less than 5, but approximately equal to 5. Okay. Now, we need to find out the swing limits. Oh, I forgot to do the VGS. Let us say that I have organized VT and I make sure that the K of this device is such that you need VGS minus VT equal to 0.2 volt. Okay, suppose, and let us say VT is 0.5 or so. So, then what is the voltage over here? The voltage over here is 0.1. What is the voltage over here? 0.1, 10 K is 1 volt. One volt drop across 10 K, you start from 5 volts, so you end up at 4 volts. Okay, that is the 4 volts is the voltage at the drain, 0.1 volt is the voltage at the source, and if I have VGS minus VT as 0.2 and let us say VT is 0.5, then the voltage here is 0.8, and you have organized R1 and R2 in that fashion. Okay. Am I being clear over here? Yeah. Okay. So, this is the DC operating point analysis, and once you are through with the DC operating point, then we need to figure out what are the limits, the maximum and minimum at the output. Okay. So, the input is going up and down around 0.8, right. Accordingly, the output is going to go down and up around 4. The drain voltage is going to go down and up around 4 volts, when the gate voltage is going up and down around 0.8 volts. But whatever happens, you want the device to be in its flat region, which means that VDS must be greater than VGS minus VT at all times. Okay. So, earlier we had the source as a static voltage, now the source is no longer static, all right. But the cool thing over here is that the source voltage is going to cancel out. VDS is equal to VD minus VS, VGS is VG minus VS. So, the source voltage really does not matter, cancels out. Okay. But V sub small d, V sub capital D is nothing but VD plus capital VD, capital VD is 4, V sub capital G is fine. So far so good. How much is VD? This is 4. Small VD is nothing but V out. This has to be more than small Vg is nothing but V in. Okay. Capital Vg is 0.8 and Vt is 0.5. So, capital Vg minus Vt is 0.3. Not 0.2, it is 0.3. Okay. And then V in is 5 times smaller, minus 5 times smaller than V out, which means that if I increase V in by 1 millivolt, V out is going to decrease by 5 millivolts, all right, or in other words this is minus V out by 5. So, now you put all the V outs together, right, what do you get? You get V out and then 0.2 times V out. So, 1.2 times V out is more than minus 3.7, or in other words V out has to be more than something like minus 3, okay, minus 3.1. All right. So, let us stop here. We will do the other condition in the next class, the other condition being the lower limit, right. What is the least value, this is the least value of V out, what is the maximum value of V out that you can tolerate, right. What is the least value of current, right, the least value of current is going to be 0. So, we will do that limit in the next class. Okay. Thank you very much.